Space weather, primarily influenced by the Sun's activity, has a significant impact on Earth and its technological systems. One of the key components of space weather is solar flares, which are intense bursts of radiation from the release of magnetic energy associated with sunspots. These flares can disrupt the ionosphere, a layer of Earth's atmosphere, leading to disturbances in radio communications and GPS signals. High-frequency radio signals, used in aviation, marine, and military communications, can experience blackout conditions on the sunlit side of Earth during intense solar flares. Another aspect of space weather is the solar wind, a stream of charged particles released from the upper atmosphere of the Sun. When these particles interact with Earth's magnetosphere, they can cause geomagnetic storms. These storms can induce electric currents in power lines, potentially damaging transformers and other components of power systems. This can lead to widespread power outages, as was the case in 1989 when a geomagnetic storm caused a 9-hour blackout in Quebec, Canada. Coronal mass ejections, CMEs, are another critical element of space weather. These are large expulsions of plasma and magnetic field from the Sun's corona. They can take several days to reach Earth and, upon arrival, can trigger intense geomagnetic storms. CMEs pose a threat to satellites in orbit, as the enhanced radiation can interfere with their electronics and solar panels. The increased drag on low Earth orbit satellites during these events can also reduce their operational lifetime. The impact of space weather is not limited to technological systems. It also has biological implications. Astronauts in space are at increased risk during periods of intense solar activity, as they are exposed to higher levels of radiation. This exposure can increase the risk of cancer and other health issues. Therefore, monitoring space weather is crucial for planning spacewalks and other extravehicular activities in space missions. Space weather also affects the Earth's upper atmosphere. During geomagnetic storms, the heating of the atmosphere can cause it to expand. This expansion increases the drag on satellites in low Earth orbit, potentially altering their trajectories and increasing the risk of collisions with space debris or other satellites. The aviation industry is also impacted by space weather. Radiation levels at high altitudes and near the poles can increase significantly during solar storms, posing a risk to flight crew and passengers. In some cases, airlines reroute flights to avoid high radiation areas, leading to increased fuel consumption and longer flight times. Financial systems can be affected by space weather as well. The precision timing required for the synchronization of financial transactions is often provided by GPS systems. Solar activity causing disturbances in the GPS signal can lead to errors in these timing systems, potentially impacting high-speed trading and other financial activities. Navigation and communication systems, crucial for both military and civilian purposes, can be disrupted by space weather events. During intense solar storms, GPS accuracy can degrade, affecting navigation accuracy. Communication systems, particularly those operating at high frequencies, can also experience disruptions. In recent years, there has been growing concern about the potential impact of extreme space weather events, such as a severe solar storm. Such an event could have catastrophic consequences for modern technological systems, leading to widespread power outages, communication disruptions, and satellite damage. The economic impact of such an event could be substantial, with estimates running into billions of dollars due to the damage and operational disruptions. Monitoring and forecasting space weather is therefore of utmost importance. Agencies like the National Oceanic and Atmospheric Administration, NOAA, and the Space Weather Prediction Center, SWPC, continuously monitor the Sun's activity and provide warnings of potential geomagnetic storms and solar flares. This information is critical for taking preemptive measures to protect power grids, satellites, and other vital technological systems. The telecommunications industry is particularly vulnerable to the effects of space weather. Satellite communications can be severely disrupted by the increased levels of radiation during solar storms. This disruption can affect television broadcasts, phone services, and internet connectivity. The reliability and quality of these services may degrade, causing inconveniences and potential economic losses. Pipeline corrosion is another lesser-known consequence of geomagnetic storms. Fluctuations in Earth's magnetic field during such storms can induce currents in long conductors, including oil and gas pipelines. These currents accelerate the rate of corrosion, leading to maintenance challenges and reduced pipeline longevity, impacting the energy sector significantly. Space weather also plays a role in the natural world. The auroras, both the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, are direct results of the interaction between solar wind particles and Earth's magnetic field and atmosphere. While these natural light displays are stunning, they are also indicators of the intense electromagnetic activity that can disrupt various technological systems. In the field of aerospace, space weather is a critical factor for mission planning and satellite operations. Satellite manufacturers and operators must design and build satellites that can withstand the harsh space environment, including the effects of space weather. This includes using radiation-hardened components and designing spacecraft with the ability to enter safe modes during intense solar storms. Global Positioning System, GPS, accuracy is another casualty of solar storms. The ionospheric disturbances caused by solar activity can lead to inaccuracies in GPS signals, affecting not only navigation but also sectors that rely on precise timing signals, such as telecommunications and financial services. Moreover, the impacts of space weather aren't confined to the present, they have historical implications as well. Studies suggest that intense solar storms in the past have left their mark on Earth, from influencing climate patterns to potentially playing a role in historical power outages and telegraph system failures. As our reliance on space-based technologies grows, so does our vulnerability to space weather. This has spurred significant interest in developing more robust space weather prediction models and mitigation strategies. For instance, power companies now use space weather forecasts to prepare for potential geomagnetic storms, implementing measures to protect power grids and minimize disruptions. Investment in research and development of space weather forecasting tools is also increasing. Enhanced predictive capabilities would allow for more effective planning and response strategies across various sectors. For instance, improved forecasts can enable satellite operators to take preemptive measures, such as adjusting satellite orbits and turning off sensitive electronics during solar storms to avoid damage. Additionally, there is an ongoing effort to understand the long-term effects of space weather on Earth's climate. While the direct influence of solar activity on climate change is still a subject of research, understanding this relationship is vital for accurate climate modeling and prediction. In the realm of international collaboration, space weather has become a topic of global interest. Countries and organizations around the world are working together to share data and resources to improve space weather forecasting and mitigation strategies. This collaboration is crucial, given the borderless nature of space weather impacts. In summary, space weather significantly impacts Earth, affecting a wide range of human activities and natural phenomena. From disrupting communication and navigation systems to influencing the natural beauty of auroras, its effects are far-reaching. The continued study and monitoring of space weather are essential for mitigating these impacts, highlighting the need for global cooperation and advanced technological solutions in this dynamic and critical field of study.